not kind of, this is exactly what's going on. This thing over here. Okay, so we have two right circular cones. One's upside down inside the other. The two bases are parallel, and the vertex of the smaller cone lies at the center of the large cone's base. What values of R and H will give the smaller cone the largest possible volume? All right, so let's write a formula for the volume of the smaller cone. Okay, so all right, so the volume of the smaller cone, well, volume of a cone in general is just 1/3 pi r squared h, I think. Yeah. All right, and then we don't know what r is. We don't know what h is for the smaller cone. So again, we're in this situation where I've got a volume equation, or I've got an equation that I'm trying to optimize, but there's too many variables. So we need to eliminate one. What we're going to do to eliminate one is we're going to notice that there are similar triangles within these cones. So if you were to sketch in, in the one cone, so I'll just draw out the big cone, I think. So here's the big cone, right? If you were to, I'm going to end up drawing this whole thing, aren't I? All right, so there's a triangle in here, like this. Okay, and the triangle, this one is set. This is the big one, the big triangle, or the big cone. So that's 6, and the height is 12. So we have this triangle here to here to here. And that's going to be similar to the triangle in the smaller cone, which is upside down, like this. And we don't know what r is here, so we'll call that r. And then we don't know what the height is here, so we'll call that h. All right, but these triangles are similar, and so we can set up a relationship between them. So we could do something, it doesn't really matter. Ultimately, we're probably going to, we want both r and h, so I guess let's just do this. So r is to h as 6 is to 12. And then again, we can either eliminate r or h. I probably should just go and eliminate h because then I won't have to square it. Let me just double check that I'm not missing anything here from the. No, hold on. All right, so I'm going to show you what I don't think it matters. I don't think it matters, but I also don't want to take the next 5 minutes and do it incorrectly because I'm missing something. So what they've done is they've set up the proportion, which is r is to 6. So they took radius to radius, which is fine. That's probably why, because we don't know that it's similar. I'm going to draw in the book. Don't tell anyone. And then they're taking this triangle right here. So essentially they're looking at big cone, which has a base radius of 6 and a height of 12. And then they're taking this triangle here. And so then this side is 12 minus h. And then this is obviously going to be r. And so the proportion that they set up from that is r is to 6 as 12 minus h is to r. sorry, 12 minus h is to 12. I misspoke. All right. Like I said, I think my way will work, but it's possible that it's possible that that triangle won't be similar to the upside down one. If you consider moving that, like shrinking that cone down, it's going to make the vertex angle wider, so it may not be similar to the triangle inside of the big cone. So I apologize for setting that up incorrectly. I'm just going to hack this, and then we'll go with the right ratio, which is r over 6 is to 12 minus h over 12. Apologize for the divergence there. Okay, so then it doesn't really matter what we solve for and eliminate. If we go for r, though, we're going to have to end up squaring like an ugly fraction. If we go for h, we won't. If you solve this for h, you get down to 12 minus 2r. All right, and so then we can drop that into the volume formula here. So v equals 1/3 pi r squared times 12 minus 2r. And it's an optimization question. We're just trying to maximize this. So we don't need to necessarily run through the derivative and everything right here. Although you could, you just distribute, and then you'd have to do the power rule twice. You should end up with r equals 4 being the value that maximizes the volume. So it's when the radius is equal to 4 feet. It turns out that the height is equal to 4 feet as well when the radius is equal to 4 feet. Questions on that one?
No, thank you.
Yep, sorry for the roundabout way of getting there. All right, 38C is the last one I've got on the list here. So all right. Motion along the line. A particle is moving along a line with position s of t. 3 plus 4t minus 3t squared minus t cubed. Find the velocity and the acceleration. And C, describe the motion of the particle for t is greater than or equal to 0. So when it says describe the motion of the particle, what they're talking about is when is it moving to the left, when is it moving to the right, and when is it stopped. I'm going to read you their answer, and we can kind of look at the graph and piece this out too, but this is what the answer is going to sound like, right? So the particle starts at position 3, moving in the positive direction, but decelerating at approximately t equals 0.528. It reaches position 4.128 and changes directions, beginning to move the negative direction. After that, it continues to accelerate while moving in the negative direction. So they've gone above and beyond what I would ever expect of you. What I would be looking for is, and the way that I typically phrase it on a quiz or a test is, when is this particle stopped? When is it moving to the left? When is it moving right? And then I might ask follow-up questions about, like, when is it decelerating or when is it accelerating? But it would all be laid out explicitly. So this is laid out really vaguely, or asked in a very vague way, as just described the motion. So your answers are going to vary widely probably there. We can quickly take a look at the graph just to kind of close the loop on this problem. So what you're given here is 3 plus 4x plus or minus 3x squared. And then last is minus x cubed. And of course, with Desmos, we can only look at the relevant part of the graph, which is when x is greater than 0. So this is what we have. So it's moving to the right as you from x equals 0 or time equals 0 to 0.528. and then it starts moving to the left. Again, you could figure that out because the velocity here is positive because the slope is increasing. And then the slope is negative here, so the derivative would be negative, implying that the particle is moving to the left. Here is a velocity of 0, so velocity of 0, and then the curve switching directions implies that the particle switches directions. And you can see that over the entire interval, it's got to come back at some point, doesn't it? Oh, it must be to the left. Over the entire interval that we're looking at, it's always concave down, which means it's decelerating.